We're going to look at the binary tree search algorithm. Now, the purpose of this algorithm is to identify the path of visited nodes to get to the search item within a tree. It also returns the reference to that node as well. We are going to trace a binary tree search algorithm, and we're going to use this as our tree that we're going to trace it on, and just break this apart a little bit just so that we understand what's going on with it. So we have our root node here, which has the value 10, and that has a reference to node 0 here. So that's what the red values indicate. They indicate the reference position of the node. We also have at the bottom there, we have the leaf nodes. You can see that there with 5, 12, and 16. So just to be really clear on this, the red values indicate the reference to the node, and then the values inside the circles are the node values themselves. This is the binary tree search algorithm code that we're going to use to trace. And you can see at the very bottom here, 14, 15, and 16, those values set out our tree. So we have the values in one list. We then have the tree left, which is a reference to the node position that goes to the left. And then the right is the same, except now it's going to the right. So it's referencing the node to the right. -1 indicates that there is no node. So for example, if you look at the example where you have left tree and right tree, where you have -1 in both of those cases, what that indicates is that you have a leaf node. So for values 5, 12, and 16 in reference position 7, 8, and 9, they are our leaf nodes, and they do not have any other nodes coming off of them. We are going to search for the value 8. That's indicated on line 17 when we call our binary tree search function. The code itself, you'll notice that it is a recursive function, so it's calling itself binary tree search there. So there are two general cases there, and also has the base case to indicate when we have found our item, we no longer need to do more recursion. So now we are going to start with our code tracing. So we're starting on line 13 here, where we set up our empty list called path. Then we set up a list of our values. So these are the values of the nodes. This is defined as a list. Then we specify our reference to the tree left. Then we specify the reference to the nodes going off to the right. Next, we make our first call to binary tree search, and the value that we're searching for is the value 8. We're starting at node 0. This is our root node. So now we are going inside the binary tree search function. Next, we add the value of the node at index position 0. So referencing node 0 is 10. So we add the value 10 to our path list. Next, we need to evaluate the if statement on line 3. Well, clearly value nodes, which is 10, is not equal to the search item 8. So that's false. Next, we evaluate whether our value is less than the search item. Well, again, because our search item is 8 and our value is 10, clearly this is false. So we do not execute the block of code on lines 6, 7, and 8, and we skip to line 9. When we do the evaluation here, we find that it's true. Our value 10 is greater than our search item. So we're now executing this block of code. Next, we check to see if the node to the left is equal to -1. Well, no, it's not, because it's actually equal to 1. So then we don't execute the line on line 11, and we jump straight to line 12. On line 12, we make our second call to binary tree search, so our second recursive call here. This time though, our tree left node, so the value of our node, the tree left, we put down as 1. And now we're going into our second call to binary tree search. So here we are inside binary tree search for the second call. Now add the value 1 to our path, and we proceed to check to see if it's the same as equal to our search item, where our search item is 8 and our value here is 1, so clearly they're not the same. So we skip to line 5. So on line 5 we check to see if our value is smaller than our search item, which it is. Search item 8, the value here is 1. So now we execute the block of code on 6, 7 and 8. We then evaluate whether the reference to our tree right node is -1. Well, it's not, because it's 3. So then we skip to line 8. On line 8, we make our third call to binary tree search with the node 3. Now we go inside the function binary tree search for the third time. We append the value at index position 3, which is now 4. So that's referencing the third reference to the third node here is the value 4. Next, we evaluate to see whether we found our search item. That's false. So we skip to line 5 and we check to see whether our search item is greater than the value itself, which is true. We check to see whether the value for the tree right node is equal to -1, but it's not. So then we make a call to binary tree search. Going inside the function for the fourth time, we then add the value. So the value we're adding here at reference node 5 is the value 8. And then when we evaluate it and compare it with the search item, well, they're equal to each other. So at this point then, we return the full path, and also we return the node position. So the node position here would be 5, and then the path here, you can see the 4 items there, 10, 1, 4 and 8. At this point then, we continue to on line 4 then, we return the path, which in this case contains the values 10, 1, 4 and 8, and we also return the node that references the item that we're searching for, which is 8, so there'll be node 5 in this case. Once we've done that, we've now finished with call 4, and we are able to hand control now back to the call 3 function to binary tree search. At this point, all we're doing again is returning from binary tree search. So we've completed everything within call 3 except for just passing back up to call 2. And at call 2, we then pass back to our call 1. Call 1, we then pass back control to our main. At this point, it prints out the path and also the reference to the node, which in this case is 5. That completes the tracing for the binary tree search algorithm.